Hello everyone, my name is Robert Moro. I'm from Slovak University of Technology in Bratislava, and I would like to present you our paper entitled Scalable Real-Time Confusion Detection for Personalized Onboarding Guides. But let me first start with the broader context of our work, which is user onboarding. Users, such as new employees, um, often need to be onboarded, that is trained to use companies' internal applications, and this costs many hours of qualified employees' time. One of the solutions to cut the costs is to apply application guides, which not only help new employees, new users, but also address the problem of adding a new functionality which is new to all existing users, as well as the problem of a less frequently used functionality, which might cause problems to more experienced users. And this solution is implemented also in the onboarding platform itself, which is developed by the company Brainware in collaboration with our university. And it looks like this. So there is a small ESLF icon in the corner of the screen, and by clicking on it, users can see the list of existing guides, of the predefined guides, and by selecting one of the guides, the guide initiates and consists of a series of these pop-ups which explain the parts of user interface or the flow of the application. And also these guides can be started automatically when a predefined rule is met. So for example, when a user visits some part of application for the first time, this predefined guide can start automatically. But the problem, of course, is that we want to show the guides only when they are needed. And to achieve this, we detect moments of user confusion, which we define as a situation in which people are uncertain what to do next. And to detect users' confusion, we use their mouse movements. However, in this paper, we do not focus on the specifics of detecting mouse detection, which we described in some of previous works, but we rather focus on the challenges of developing a production-ready confusion detection module. And in so implementing such a module, we had to develop, because we use mouse data to detect user confusion, we had to develop a real-time scalable mouse logger. We had to develop a system that would be able to detect confusion leveraging domain-specific classifiers. That is, we want to have multiple classifiers, each trained for each custom application. And since we want the detection to be in real time, the system has to have a fast feedback loop for confusion detection. And also, since we want to maintain several models, one for each custom application, we need to have a way of retraining the model in production by using or gathering the implicit user feedback. So this is how our proposed infrastructure looks like. The ESLF itself consists of these two main components. So client component, which is loaded into any custom web application using a JavaScript snippet, is responsible for showing the list of guides and the guides themselves, as we saw on one of the previous slides. And the guides are stored on the guide server, which then communicates with the client, sends them data about the guides using a WebSocket server. There is actually a third component called the ESLF editor, which is used to define the guides and to define the rules when these guides should appear. In this work, we extended this infrastructure with these components responsible for detecting confusion, which I will talk about in more detail on the slides. So, as I said, we use mouse data to to detect confusion. So we implemented a mouse logger that runs on the client side, and it is an event-based mouse logger, which means that we capture all mouse events in a browser, and these are stored on the client into batches, and then these batches are dispatched to the ESL logger server, which stores them into Elasticsearch cluster. Logger server also counts the number of mouse events, and if limit is reached, it fires limit reach event, which initiates confusion detection. Now the most important part of our solution is, of course, confusion server. So it receives, it's subscribed to the limit reach event, so it receives this event which initiates confusion detection, and then it does several things. First, it retrieves a pre-trained machine learning model from Elasticsearch cluster, which is trained for that specific custom application. And it also retrieves the last n seconds of user mouse data, which is also stored in the Elasticsearch. Then it preprocesses this data to be suitable as an input to the retrieve classifier, and classifies whether the user is or is not confused. If there is a positive case, so the classifier classifies user as confused, it fires confused event, which is again sent to the message queue. And for each application, there is a dedicated model. If a confusion event is fired, it starts or initiates ESL confusion intervention. So guide server receives the confused event, and it propagates it using a WebSocket server to the client, which then reacts by shaking the ESL context help for the confused users, or alternatively it can pop up a question asking whether user needs help. If the user clicks on the shaking button, shaking context help, he or she is asked whether he or she is actually confused, and after selecting yes, the list of guide appears, and it is possible to initiate one of the defined guides. Now the main challenge is that confusion detection approach is context dependent. That is, we need to train separate confusion classifiers for each custom application and store these trained models in Elasticsearch. So we decided to enable this dynamic model retraining to analyze user interaction with the context help, and to use this interaction, this implicit user feedback, to label data. So if the context help shakes or questions up, there might be no interaction at all. So the user decides to ignore this, in which case we would label this as a false positive case. So we thought that the user is confused, but he or she is actually not confused. But he or she might decide to click on the shaking prompt, shaking context help, in which case a list of guides appear, but it's a stronger signal, but still not strong enough, because it might have been only from the curiosity. So then we see if the user actually opens one of the proposed guides, and then whether there is any user interaction with the guide. So whether user goes through some of the steps, at least some of the steps of the defined guide. And the strongest signal is if the user actually finishes the guide that was initiated after being detected as is confused. And in these two last cases, we would label the data as a true positive case. That is, user was detected as confused, and he or she is really confused. The problem is how to get false negative cases. So that is cases when users are confused, but we do not detect that. One of the possible solutions how to get these labels is to log when user click on the context help but no prompt is presented to them. Or alternatively, we might ask them questions from time to time whether they are confused, but this might be lower user experience, so it's not suitable for each application. Okay, so as I said at the beginning, we integrated the solution into the production environment. So each component that I described is implemented as a separate dedicated Docker container, and this means that all services are easily scalable by running on multiple hosts. At the moment of writing the paper, there were 3 customers that actively used our confusion detection module in ESL with more than 200 concurrent users. Now there are even more. There are 5 companies that use the solution. This figure shows the scalability of our logger solution. So we can see that there is up to 2,500 mouse events stored in the Elasticsearch in a 30-second window. So this is really not a bottleneck, and it is implemented in a way that it does not overload or does not put too much strain on the client or on the server. And this figure shows the number of predictions that are made per day, which is up to 10,000, which is approximately 1,000 predictions per 1 working hour. And of course, it does not say whether the predictions were correct or not, but from the data that we observe, we can say that the users benefit from having confusion detection on because they spend less time on the screens and they are more efficient in achieving their goals in the application. To conclude, we focused on this work on the production deployment of emotion detection systems. In our case, it was confusion detection, which is accompanied by many challenges which are poorly addressed by the existing works. Our main contributions lies in tackling these problems, and we demonstrated in the paper the capability of our solution to scale and provided analytical insights to the logging component of the module. The biggest limitation right now of the system is the performance of the confusion method itself. According to our previous works, it achieves results which are comparable to the state-of-the-art solutions, but it is very context or application dependent. So we need to train models for each separate custom application. And to address this problem, we proposed and developed a model retraining mechanism based on the implicit feedback of the users, which is currently being evaluated. And we also plan to more closely examine the ways of prompting to confuse users. So now we have 2 ways of either shaking a button, shaking the context help, or asking the user whether they need help. And we want to examine how this influences the user experience, so which way is better. That is all, and thank you for your attention.